Now that we've looked at proving various trig identities using known identities, we'd like to take a look at some additional identities for trig functions, sort of universal identities that are quite useful for, for a lot of different things, but in particular for evaluating trig functions at different values, for simplifying problems that have trig functions in them, all kinds of different things. And in particular, what we are going to look at today is the kind of identities that are known as sum and difference identities. Now, these deal with problems like, how can you compute, let's suppose that I ask you to, let's say that alpha and beta are a couple of angles, and maybe we know sine alpha, sine beta, cosine alpha, cosine beta, so we know these trig values, okay, then can we say something about what is the sine of alpha plus beta, or the cosine of alpha plus beta? And the same thing we could do if we wanted to do minus. So what if we wanted to take the difference of these angles instead of their sum? Okay, so we want to establish something that we can say about what these values are. And I'm going to show you two different ways of proving these things. They're going to, the first half of this video is going to be sort of the geometric proof of some of these properties. And then we're going to talk about a technique that relies upon something called Euler's identities. The issue is that in order to establish Euler's identities, you need to use some calculus. So there's going to be some things that I have to say about Euler's identities that you're just going to have to take on faith for the moment. But first, let's talk about the geometric proof here. All right, this geometric proof that I'm going to give you is a little different than the one that's in the books. Now, the advantage of the one in the books is that it works for any angles. The one that I'm going to give only works for alpha and beta that are between 0 and pi over 2. However, this proof, I think, is a lot easier to understand what's going on. And essentially, once you have it for the angles between 0 and pi over 2, you can kind of mess around and figure out, well, it holds for the rest of them as well. I mean, you can use the other proof instead if you want to, but once you have this established for 0 to pi over 2, it turns out that's all you need in order to apply Euler's identities and things like that. So, the construction that I would like to make here, I am going to make a large rectangle that initially is going to seem a little bit weird, but we're going to see exactly why I want to make this rectangle in a moment. Now, I want to make this rectangle such that I put this line here from the lower left corner over to here, and we're going to make that angle alpha. Now, we can just do that wherever it happens to be. And we will see exactly where, actually, I'm going to leave the top of this rectangle open for the moment, because that's actually something I want to add later. So I don't know how tall I want this rectangle yet. Now, from this line, I want to make another line here that has an angle of beta, but not an angle of beta with the base of the rectangle. I want the angle beta to be between this line and that last line that I just drew. And this is also going to tell me how tall to make this thing, because I want this line segment to have a length of 1. And then I'm going to cap the rectangle so that this line segment has a length of 1. Okay, so that tells me how tall this rectangle should be. I drew this poorly. I'm sorry. That was drawn at not quite the right spot. So this line segment over to this perpendicular should have a length of 1. Yeah, sorry. I said that a little bit poorly there. I want this line segment to have a length of 1, and it needs to, at this point where we hit a length of 1, it has to meet this perpendicular line here. Okay. Sorry, that was my bad. This construction is a little bit weirdly complicated, so I drew it incorrectly the first time. So now that we have this established, really everything that we're going to do from here on out is going to be just a matter of labeling what are these various pieces. How long are they? Well, there's a few things that we can say right off the bat. For example, I can say that the length of this side is sine beta. Okay, that's a terrible looking beta. Let's make a slightly better beta. So that side is going to be a length of sine beta, and this side is going to be a length of cosine beta. The bottom here is therefore going to be cosine alpha cosine beta, because the hypotenuse of this bottom triangle is cosine beta, and the adjacent side is hypotenuse times cosine alpha. So cosine alpha times the hypotenuse, which is cosine beta. Similar argument shows me that this side here is going to be the sine of alpha times the cosine of beta. So that's just this segment right here. Let's see what else we can say here. Well, one thing that we can say is that using some arguments from trigonometry, we can say that this angle up here is going to be pi over 2 minus alpha. That makes this angle, it's going to be pi over 2 minus alpha minus pi, or I'm sorry, it's going to be pi minus pi over 2 minus pi over 2 minus alpha. That makes this come out to be alpha. Now, because this is a rectangle that we constructed, that is a right angle. And that means that we can label the lengths of these pieces as well. So this segment here is going to be cosine alpha times sine beta, because sine beta is actually the hypotenuse of this upper right-hand triangle. And the top here is going to be sine alpha sine beta. This little piece here. Okay, now, you're probably wondering why we're doing all this, because we still haven't really worked in alpha plus beta. Well, here's where things get good, because the whole reason for doing this is we have these three triangles, but we have a fourth triangle that we've got sitting over here, okay? And what is this fourth triangle going to look like? Well, this angle up here, if I use the same kind of argument that I did to find this angle, I can see that this angle is actually alpha plus beta. And that is good, because that means that when I find the dimensions of these sides, that's going to tell me something good. Because take a moment here and see if you can figure out what would these be in terms of the trig functions. Well, this is the opposite side, and the hypotenuse of this triangle is 1. So this left-hand side is just sine of alpha plus beta. And this top here is going to be cosine alpha plus beta. Okay, so we have this enormous kind of mess here, but the good news is this actually tells us the sum identities. Why does it tell us the sum identities? Well, because I can compare the length of the left-hand side and the length of the right-hand side. This is a rectangle, so the left-hand side and the right-hand side have to have the same length. So that means that the sine of alpha plus beta has to be equal to the sum of these two lengths, which is going to be sine alpha cosine beta plus cosine alpha. Whoops, that's a sine alpha. I meant to write a sine beta here because this is a beta. Okay, so we now have established this identity, at least for alpha between 0 and pi over 2. Now, like I said, it actually turns out that with a somewhat more complicated geometric construction, you can prove this in general. And the book gives you a more general proof of this fact. What about for cosines? Well, the cosine of alpha plus beta, that's going to be a little bit harder to figure out. But it's still not super bad, okay? It's still reasonably simple to do. The cosine of alpha plus beta is this segment. Well, the length of this segment here is the length of the bottom, which is cosine alpha cosine beta, minus the length of this segment here, which is sine alpha sine beta. And this establishes the identity that we want for alpha plus beta, for cosine. All right, so I'm going to erase this now. Now, don't worry too much about, memorizing that whole proof or anything. I'm not going to ask you guys to prove it or anything like that in this class, but I think it is good to see where this comes from. Using this, we can also work out what happens if you were to subtract the angle instead of adding it. So what if I wanted to do sine of alpha minus beta? So assuming that we have established this for any two angles, then what we can do is we can say this is the same as the sine of alpha plus negative beta. Well, that's going to be equal to sine alpha cosine minus beta plus cosine alpha sine minus beta. Okay, what can we say then? Well, we know how to deal with these two things because we know that cosine is even, meaning that the negative can be taken out of the function and it just disappears. So this becomes sine alpha cosine beta. And sine is odd, meaning that this negative comes out front and makes the whole expression negative. So we subtract cosine alpha sine beta. And this gives me the difference identity for the sine function. I can summarize both of these together in a nice way. I can actually write sine of alpha plus or minus beta is equal to sine alpha cosine beta plus or minus cosine alpha sine beta. It's a good idea to actually memorize this formula, this expression, okay? It's something that you end up using reasonably often. Now, of course, a lot of the stuff that you'll be doing online, you can always refer back to it, but if you ever need to use this stuff frequently, it's a good idea to kind of memorize this thing. Before we go on to talking about another way of establishing this stuff, I want to, for a moment, go ahead and look at what we can say about the cosine of alpha plus beta. Well, or I'm sorry, the cosine of alpha minus beta, because we already know the cosine of alpha plus beta. So what if I wanted to do the cosine of alpha minus beta? Well, this would be, using the same kind of reasoning, cosine of alpha plus negative beta. Now, challenge for you guys. Pause this for a moment and see if you can do what we did for the case of sine, but do it for cosine and see if you can work out a similar formula. All right, hopefully you guys were able to figure that out using the even and odd properties, but let's go through this and make sure that everybody sees what's going on here correctly. So this is going to be the same thing as the cosine of alpha times the cosine of minus beta minus the sine of alpha times the sine of minus beta. But by the same kind of reasoning as we did before, using the evens and odds, we can say, well, this left-hand term becomes cos alpha cos beta, and this right-hand term becomes plus sine alpha sine beta, because the negatives now cancel with each other. And we can summarize this, once again, in a fairly nice way by saying that the cosine of alpha plus or minus beta is equal to cosine alpha cosine beta minus or plus sine alpha sine beta. So notice the thing you got to remember is that the negative flip-flops in the case of the cosine. It does not flip-flop in the case of sine. And we get these two nice formulas. So take a moment to make sure that you have those written down where you can easily refer to them. All right, so sorry, I had to take care of something really quickly there, so I paused this while I was going. I want to show you an application of these things that you could also probably get from some fairly simple geometric argumentation here. But let's suppose that I wanted to know, well, what is the cosine of pi over 2 minus theta? Well, this would be equal to, by what we've written down here, this would be equal to the cosine of pi over 2 times the cosine of theta, and then I would get plus sine pi over 2 sine theta. But the cosine of pi over 2 is 0, and the sine of pi over 2 is 1. That means that this comes out to be the sine of theta. This is actually something that you can see easily enough if you think about the triangle description for the trig functions, because think about if I have some angle theta, let's say that I have a triangle with a hypotenuse of 1, here's theta. Well, this angle up here is pi over 2 minus theta. And this side over here is the sine of theta, but it is also the cosine of pi over 2 minus theta. So if you think about this in terms of triangles, this identity is exactly what you would expect. But it's good to see that we can also get it from this kind of an argument. And if you think about this triangle, then the bottom side here is going to be the cosine of theta, but it's also going to be the sine of pi over 2 minus theta. So you probably expect you get a similar thing going on in general for sine, and that is true. If we take sine of pi over 2 minus theta, this becomes equal to cosine of pi over 2 sorry, I was for some reason looking at the top formula here instead of the bottom formula. This becomes sine of pi over 2. I was wondering why I was writing down the wrong thing. I was like, no, that should be a sine. It's because my eye was drawn to this top line here instead of the bottom line, and I just started writing without thinking. Yeah, so this becomes sine of pi over 2 times cosine of theta, and then we're going to have minus cosine pi over 2 sine theta. But once again, this is 0, so this term goes away, and this is just 1, so we are left with cosine theta. So these two identities are actually good identities to remember in general. Personally, I find them easier to remember just by thinking about right triangles, but you should be aware that they are true for all angles, not just angles between 0 and pi over 2.